Hello and welcome. This is Miss Wiesen, and we are starting Unit 3 today. Unit 3 is on intermolecular forces and properties. So let's go ahead and title our notes Unit 3. Remember, we are not going to throw away our notes. We'll have them all year as a reference point. And so what that means is you should have the Unit 3 note guide. You should have a writing utensil, your calculator, which probably you'll need later on in the unit. And if you need extra paper to take additional notes on, then please do so at this point. It's worth mentioning that upwards of 22% of the AP chemistry exam in May will come from topics and concepts that you're going to see in this chapter. So it's very important. And what that means is I'm going to spend a lot of time up front in this first podcast, really getting into some of the details about what we're learning, and that is intermolecular forces. So you're going to see a lot of cross-pollination of topics throughout the year. Well, what this means is that you should recognize a lot of this stuff from previous units or even the previous year of chemistry, but then you will also see a lot of new stuff. And ultimately, what we're going to talk about to begin with, to start, is states of matter and how these molecules start to stick to one another. Now, that's not the language I want you to write about, but it's certainly something you can start thinking about. And we're going to get into some pretty fancy vocabulary to improve your language. And in this chapter, I'm going to also load you up with a bunch of synonyms because I'm going to need you to be able to answer those AP questions in May. Because at the end of the day, that's really what it boils down to, the most important thing. You want your AP credit, and I don't blame you, and you put a lot of effort in, and you deserve it. So let's get into it. Now, it is time for us to consider the forces that are responsible for condensing matter. All right, and before we start, let's take a look at a basic phase change diagram. A lot of the language here you should be familiar with. For example, if we're going from a solid to a liquid, we refer to that as melting. Anyway, I'm not going to read this for you, but I would mention that the two that are a little bit more obscure that you may not remember is the process of sublimation, where a solid will bypass the liquid stage and go straight to a gas. And consequently, a gas going back to a solid is called deposition. In my experience, those are the more obscure ones that you may just need to re-familiarize yourself with. All right, so if we take a look here at the image at the top of the page and we see the gas phase, the liquid phase, and the solid phase, let's go ahead and start with the gas phase. Now, gas molecules are in constant motion, and in fact, all states of matter have some degree of motion or rotation or vibration. But when it comes to gases, these guys are going to be the least condensed of all the matter. And when we actually take away the thermal energy within a gas system, a gaseous system, those molecules will actually start slowing down. And when they start slowing down, they possibly can start feeling more force of attraction as they move past each other. And again, because they're not moving as fastly, they can possibly start feeling force of attraction between the like gas molecules. Now, when this happens, we will serve to liquefy or to condense that gas into its liquid state. And remember, going from a gas to a liquid is called condensation. And one more time, if you're going from a liquid back to a gas, we call that evaporation, or sometimes we even say boiling, or sometimes we even say vaporization. Let the synonyms begin, you guys. And again, all these molecules have vibrational motion. Even solids, if you take a look over here, solids even have vibrational motion, which means that the solid itself will vibrate in a fixed position. One other thing, though, that's different from a solid, and as we compare it to gases and liquids, is that gases and liquids are going to have something called translational motion. Translational motion. Okay. Now, if you think about the word trans, it simply means across. And so this means that molecules that are in the liquid and gas state have the ability to really move about. Okay. They actually have an ability to move to different locations within the container or the system that they're being held in. So if we go back to this example here that we're talking about, when we condense a gas to a liquid, Okay. If we continue to remove thermal energy from that system, eventually that liquid will be turned into a solid, will be condensed into a solid. And so what we're going to look at is how all of this works. The very short answer right now, you guys, is intermolecular forces. And we're always going to abbreviate intermolecular forces as IMFs. I think it's just going to be a lot easier when we're answering questions on the free response portion of the AP test. They are and will accept the abbreviation IMF, okay? So intermolecular forces, or IMFs, are the forces that are going to hold one molecule to another. They are not bonds, okay? These forces essentially arise, you guys, from an unequal distribution of electrons within a molecule. So in other words, electronegativity and polarity are going to come back up again, all right? So we're going to talk about how these forces between molecules arise. And we make a note that when we are talking about intermolecular forces, that is not the same as a bond. All right, so one thing that can kind of help you with this is if you look at the prefix inter, that simply means between molecules, okay? And I want you to also know that intra means within. So here is one thing that you could say. A bond, for example, if you look down here at the hydrochloric acid molecules, there's two of them. What we see here in this image is an example of an intramolecular force. Again, an intramolecular force, you guys, is really the same thing as a bond. So a bond is within the molecule. It's actually holding the molecule itself together. And that is exactly what we are not going to talk about this unit. Instead, we are going to talk about intermolecular forces, which are not the same things as bonds, and again, are the forces between molecules. So you can kind of look at this picture of hydrochloric acid, two HCl molecules, and they're showing how hydrogen and chlorine are forming a covalent bond, but the forces between two HCl molecules are, in fact, what we're going to be focusing on this unit, the intermolecular force. Now, one thing you need to know is that bonds, intramolecular forces, are exceptionally stronger than intermolecular forces, okay? Now, I know a lot of you are math kids out there, and, you know, I'm a math kid. Well, maybe not, I'm a math old lady, and you get what I'm saying, though. And if you look at this image here, this intermolecular force image of two hydrochloric acid molecules, the energy holding the intermolecular force together right here is about 3.3 kilojoules, okay? Where the covalent bond over here, the energy holding this covalent bond together is going to be, I don't know, about 130 times stronger. And if you do the math, that's going to be roughly 500 kilojoules of energy that you would need to apply to break that covalent bond. So one thing to get clear is that bonds are much stronger than intermolecular forces. But intermolecular forces, because they cause state changes and because they're responsible for a lot of the physical properties of substances, we will have an entire dedicated unit talking about these. To indicate a partial charge on the side of the molecule. So let's look at the image still here. We're on the hydrochloric acid molecule. And I know that chlorine is going to pull on the electron of hydrogen, making this side partially negative. And because most of the negative charge is over there, that will consequently make the hydrogen side partially positive. Well, if you do the same kind of annotation to the other hydrochloric molecule, so let me do that. What do you notice? You notice that the force of attraction between the molecules, so that intermolecular force, is caused due to a opposite charge force of attraction. Now, when you see the partial symbol, like partially negative and partially positive. It's really important to understand that's not a full-on charge like you would see in an ion. So here's the thing. Things like melting point, boiling point, density, solubility, vapor pressure. These are all physical properties of substances that we can ultimately determine and predict based off the types of intermolecular forces that are found within those substances. And so hopefully our goal by the end of this is that we can actually look at a substance, predict what types of intermolecular forces they may have, and therefore predict some of the physical properties that we would expect to see arise from certain substances. So before we move on, at the end of the day, if I ask you to take liquid water and to boil it into its gaseous state, I'm going to say right now that you are not breaking the bonds of the water molecule, but rather you're breaking the intermolecular forces between the water molecules. Okay, really important concept to nail down right now. So stay with me here. In order for a state change to occur, one more time, we are not breaking bonds. We are simply overcoming intermolecular forces. So, as I just mentioned, the physical properties of substances are really attributed to the strength of the intermolecular forces that that substance has. All right, let's look a little bit more into how this actually works. So generally speaking, if substances have weak IMFs, they're going to have low boiling points, lower melting points, lower vaporization pressure points. And if a substance has stronger intermolecular forces, the opposite is true. They're going to have higher boiling points, higher melting points, higher vapor pressure points, etc. So let's talk about maybe gasoline. All of you have smelled gasoline before and probably know exactly what it smells like. Well, gasoline evaporates pretty easily, which is one reason why you can smell it when you're pumping gas into your car. Gasoline evaporates much more quickly than, say, water. So we can say that the intermolecular forces that hold gasoline molecules to one another are much weaker than the forces that hold the water molecules together. So, are you with me? On a warm day, this would provide enough thermal energy to break the intermolecular forces between gasoline molecules, thereby converting it to its gaseous state, and that's actually when you can start smelling it. Now, before we go any further, let's go ahead and do exercise problems 1 and 2 so we can just get some practice with polarity and allow us to make some clear definitions between a bond versus an intermolecular force. And so let's go ahead and read the question. Exercise 1, circle all of the molecules that are polar. Do you remember how to do this? Remember, you need to know something about electronegativity, and you need to draw the dang Lewis dot structure. When in doubt, always draw the Lewis dot structure. So if we take a look at A, I'm going to go ahead and just draw the Lewis dot structure out really quick. Okay, so if we take a look at CH3Cl, you can see that chlorine is going to be more electronegative than the carbon it's attached to. And so therefore, chlorine is going to be more electronegative than carbon. It's going to pull the electrons towards it, making that side of the molecule partially negative. Now, conversely, the other side of the molecule would likely be partially positive because most of the negative charge is hanging out next to chlorine. So let's go ahead, and before we can answer the question, we need to do the Lewis dot for each. Here is CH4, which they call methane. The Lewis dot structure for CCl4, which I'm sure we've done in class or in our notes. It just seems familiar here. So let me go ahead and jot the Lewis dot structure for that down as well. Let me draw the lone pairs on here. And again, if you want to confirm that I'm doing all these Lewis dot structures correctly, just follow the process of doing Lewis dots and do them on your own. In fact, I would always encourage you to pause me, try the exercise problem before I do it, and then that way you can kind of compare and check your answers. All right, SO2, we're now on the last one. The Lewis dot structure I get here, and it looks like this has potential for resonance. But the point being is that getting just the Lewis dot structure down will help us regardless. Now, take a look here. We've got sulfur and 2 oxygens. Which one of these molecules is more electronegative? Remember your trends. It's oxygen. That's right. Oxygen's going to pull in the negative charge from sulfur. And what's going to happen then is it's going to make the oxygen side of the molecule partially negative and the sulfur side of the molecule partially positive. And so I would say that in going back to option B and C, we really would not have at the development of a polar molecule. Now, some of you are going to argue that if you go to CCl4, if you go back to option C, that all of those chlorines are electronegative and they're all pulling the electron towards the chlorine molecule, which should be a negative, which you're right. But what's happening here? What's happening here is if you draw the dipole moment or the direction of the charge, it would, remember we draw a line and we point it that way. So this carbon here coming off of this chlorine would be going that way. This carbon to this chlorine would be going that way. And if you draw the direction of the charge on the last one, it would be going that way. What do you think is going to happen? This is going to cancel out and there will be no dipole, okay? And therefore the molecule will not be polar. So right now, if I had to choose, option A and option D would be the best option. All right, exercise number 2. It says, explain the difference between a chemical bond and an intermolecular force. Compare the relative amounts of energy involved in the forming and the breaking of each. Okay, so why don't you go ahead and put me on pause? I'm going to jot down my response. You could do the same. Come back and compare your answer with mine. Okay, sorry for the chicken scratch here. I do a lot of abbreviating, so if you are confused, then please bear with me. So a chemical bond is formed between atoms within a molecule, and intermolecular forces are formed between molecules. One is within, one is between. And as we mentioned earlier, chemical bonds are going to generally be a lot stronger in terms of energy involved in their formation than an IMF. Okay. On top of page 2, we're actually going to start getting in and talking about the different types of intermolecular forces. Okay. And what we're going to do is we are going to talk about the weakest types first and work our way to the strongest types of IMFs. So one more time, when you are looking at this, it's important to delineate that we're going to start off by talking about the weaker forces and progressively going to the stronger ones. And I'd like to make a caveat here. We're trying to rank IMFs in terms of strength, and this is relative. In other words, we have to be comparing molecules of similar size, of similar electron density, if you will. So please keep that in mind. For example, if we compare a small molecule to a giant one, that's not going to be fair. And what we need to do is that when we're talking about strength of IMFs, it's all relative to samples of similar sizes. Okay. So this is getting ready to be a big vocabulary lesson for you. It is very conceptual, and this means you really have to sink your teeth again into these concepts. So what we have here is the weakest type of force. We call this a London dispersion force. And oftentimes you will hear them just be referred to as dispersion forces. All right. And there's even more names for these. But right now, I think if you went with London dispersion force, which we abbreviate as LDF, again, you're allowed to abbreviate London dispersion forces as LDFs. That is allowed on the exam. Now, guarantee you're going to have a question about this because this one is very important. And essentially, this is an intermolecular force that exists between every type of substance and every type of molecule. So if you are asked what type of IMFs a certain substance may have, one type of IMF that you will always be certain that it has is an LDF. And that's because every substance has London dispersion forces. Let's take a look on a molecular level what's happening here. You're going to start here left. I'm going to circle this image and we're going to work our way right. So when you're looking at this image, that is the correct way to view this. It's important to notice that we are starting off with 2 nonpolar atoms sitting next to each other. Okay, you see them here represented as gray spheres. And what's going to happen is something in the environment is going to cause or perturb, which basically means disrupt or disturb, is going to perturb that substance. And maybe it's a magnetic field, maybe it's a drastic temperature inversion, maybe it's a violent physical agitation of the substance. It could be a number of things that causes the disruption. Now, look at what happens. After the substance has been disrupted, you're going to get something called a momentary or temporary movement of electrons within those molecules, those nonpolar atoms or nonpolar molecules. And so, again, that's the middle picture that's being indicated here. So some outside force has disrupted the sample to create an imbalance in charge within that molecule. And you can see that in this middle image, one side of the molecule is negative and one side of the molecule is positive. Again, this is temporary. If we are leaving that sample back to its normal conditions, it would resettle back into a normal nonpolar atom. But again, since we've disrupted it and created some type of agitation, it's created a momentary or temporary dipole. Now, what you should notice here, and I'm going to circle it in the image, is that when these two negative charges get close to each other, what's going to happen? That's right, they're going to repel each other. And so once they repel each other, the molecule itself is going to spin around to orient itself in such a way that the positive side of one of those molecules is going to orient close to the negative side of the other molecule. And so what happens here is this very weak force called a London dispersion force between these two molecules. Okay, so now let's go down. So that's the weakest one, you guys. Let's go down to one that's just a little bit stronger. Again, vocab here, hardcore. This one is called a dipole-induced dipole. This is, again, I'll say it one more time, the second weakest next to LDF. And in this particular scenario, it's going to involve a polar molecule next to a non-polar molecule. And one of the things that I want to draw your attention to is, I'm going to circle it here in your notes so you can see that in each one of these situations, I have included a diagram that will help you visualize what each IMF is. Now, again, I'm going to say it one more time. You're going to have some type of nonpolar molecule, and I just circled that. So this is a molecule that has no dipole moment. It's nonpolar. And so let's say this nonpolar molecule is now placed next to a polar molecule. And so that brings us to the second image. And so what has happened is that the molecule that was originally nonpolar, and I'll highlight it for you. This was originally nonpolar, but look at what happened. We went ahead and put a water molecule or a polar substance next to the nonpolar molecule. So what do you think that's going to do? Well, since water is polar, it's going to have a partial positive and a partial negative side. And when that is placed next to a non-polar molecule, it's actually going to induce a dipole in the otherwise non-polar molecule. And you can see here, it's kind of hard to see, but this water molecule, its partial negative side is going to align to the partial positive side. But this negative side is actually going to repel all of the electrons over to this side of the molecule. Does that make sense? And so what happens here is you are going to have the more positive side orient itself to the more negative side of the water molecule. And that attraction in between the two is called an dipole-induced dipole IMF. And the vocab you're going to need to use here is this word polarizable. I'm going to highlight it, polarizable. So the thing to understand here, you guys, is that if we get larger and larger molecules, okay, in other words, molecules that are going to contain more electrons, they're going to have the ability to become more polarizable. We also say they have the ability to have more polarizability. So another term you're going to need to constantly use in your responses is polarizable. And sometimes you can even say polarizability. All right, the third type of intermolecular force is called an ion-induced dipole. an ion-induced dipole. Again, let's go over here to the image. And each of these definitions I'm speaking on, I'm not necessarily reading them verbatim, but you can go back and read exactly what I wrote here. But if you go over here to the side, I'll go ahead and circle it. This image here is an example of an ion-induced dipole. So let me go ahead and erase this. This is when one of the molecules is a true ion, and it's going to be in the presence of a nonpolar molecule. So if you take a look at this first image, it's just the nonpolar molecule kind of hanging out by itself. And then you take a look at the second image. We went ahead and introduced, it looks like a cation, so some positive ion here. And so what's going to happen is this positive ion, when it comes close to the otherwise nonpolar molecule, again, it's going to induce a dipole effect in the nonpolar molecule. And so let's go ahead and conceptually make sure we understand what's going on here. So if this cation approaches a nonpolar molecule, what's going to happen is it's going to force all of the negative charge, it's going to force all of the negative charge to the opposite charged ion. So all the electrons will come to one side of that nonpolar molecule and consequently will be attracted to the cation. Okay, so this little force in between the two, it's not a bond, it's just a force, is what we call an ion-induced dipole IMF. You guys are able to pick up what the word induced means. Okay, induced. Again, more vocabulary. Have you ever heard of a woman being induced for labor? Well, you probably have. In this case, we're forcing contraction so the baby can be delivered. Well, in this case, in chemistry, the ion is actually forcing the electron cloud of the nonpolar molecule to shift its charge about within that molecule. And so if you remove that ion, that nonpolar molecule would go back to its normal state. So induced means to force. You might want to jot that down. All right. One of the stronger types of intermolecular forces, and the fourth one, is what we call a dipole-dipole. Okay. And really, arguably, dipole-dipole IMFs can technically be considered the strongest type of IMF. And you'll see that below it, we put something called a hydrogen bond. We'll talk about that and clarify here in just a second. But let's look at what a dipole-dipole is. Dipole-dipole IMFs occur when you have two polar molecules. Again, two polar molecules. Go over to the right. You're going to see that there's an image there that helps us illustrate this. So let's zoom in on it. And it looks like image A is where we would start. And sure enough, it looks like we've got two polar molecules. The positive side of one polar molecule will be attracted to the negative side of another polar molecule. Again, this force of attraction is called a dipole-dipole IMF. It is one of the strongest types. These substances, or substances that have dipole-dipole IMFs, are going to be the substances that have the higher melting points, the higher boiling points. And that is because since these are strong IMFs, we expect for them to have more of those higher robust physical properties, okay, compared to substances that have weaker IMFs. Now, if polarity still mystifies you guys, then I would suggest you get the clarification before moving on. You could try to do that by going back and revisiting previous podcasts, or going back and reading your textbook, and going back, and in the first two units, we did bring up polarity. Now, the strongest IMF of all is a type of dipole-dipole. And this is what we call a hydrogen bond. Now, if I could change anything in chemistry, I would rename this. Hydrogen bond is going to serve to confuse you because you're going to think this is an actual bond. I'm going to let you know right now, this is a really bad name for this IMF because it's not a bond. It's an intermolecular force. So a hydrogen bond, an intermolecular force, is not the same as a bonded hydrogen. Let me explain, okay? One thing that's going to help us understand when a hydrogen bond is going to form is to remember our three most electronegative elements on the periodic table. fluorine, oxygen, and nitrogen. And see, here's what's going to happen. The hydrogen in one molecule is going to be attracted to the highly electronegative fluorine, oxygen, or nitrogen in a neighboring molecule. If I have a water molecule, HOH, okay, do you guys see one of the most highly electro atoms, a part of water? Yep, oxygen. Well, what if we had another water molecule come in close proximity? Okay, sorry about my drawing here. Let me write this better. Okay, well, what do you notice? We notice that this hydrogen of one molecule and the oxygen of another molecule are actually going to form a hydrogen bond. Again, that is it's not a bond, it's an intermolecular force. So a hydrogen bond is not the same as a bonded hydrogen. When you hear the word of a neighboring molecule, a molecule next door or really close by, oftentimes you'll see the word adjacent. So adjacent and neighboring are synonymous. Yay, there's more synonyms. So more information on IMFs. Again, lots of concepts here. IMFs are a function of the number of electrons in a given molecule. In other words, polarizability. Larger molecules have more electrons and have the ability to create stronger IMFs due to that. Molecules are also in constant motion. They're surrounded by other molecules or colliding with other molecules. And so when these collisions occur, those electron clouds would oftentimes be perturbed or distorted or disturbed, whatever word you want to use. And again, the amount of distortion of the electron cloud is referred to as polarizability. So let's do exercise 3. It's asking us to list the IMFs that would exist between each molecule. Circle the strongest force if the substance has more than one. Hint, again, when in doubt, draw the Lewis dot structure. This will actually help you see polarity, which will help you determine IMFs. And so let's do a couple of these. I don't think we could spend a lot of time doing all of them. It would chew up a lot of time on this already long podcast. In the previous one, we already drew CH3Cl. Remember, we had carbon with 3 hydrogen coming off, and then this chlorine with lone pairs. And we knew that the chlorine was more electronegative and will pull electrons, making that side of the molecule more electronegative. So if I were to place another CH3Cl molecule next to it, I know that this hydrogen side would be partially positive. A force of attraction would occur. Now, what are these molecules? CH3Cl, are they polar molecules? If you said yes, then instantly you know they are going to have dipole-dipole. Now, most of you would say, oh, this is a hydrogen bond. Well, no, hydrogen bonds are only defined as hydrogen forming an intermolecular force with fluorine, oxygen, or nitrogen only. In this case, hydrogen's forming an IMF with chlorine. So we just refer to that simply as a dipole-dipole. And then, of course, LDFs are here because every substance has London dispersion forces, which is the weakest type. And if there's any questions, we can go over these in class. Exercise 4. Put true or false. If it's false, change the underlined word to make it true. Okay, IMFs determine metallic properties such as the boiling point of a substance. The answer would be false. It's not metallic properties, it's physical properties. Okay, next one. True or false, IMFs are forces of attraction between atoms. Patently false. No, they are forces of attraction between molecules. The forces of attraction between atoms, those will end up forming bonds to form molecules. Okay. All right, chemical bonds are the forces between molecules. That sounds true to me. Fourth one, IMFs, intermolecular forces, result from the electron interactions between neighboring molecules. And that sounds like a good definition to me. True. And the last one, chemical bonds include ionic bonds and hydrogen bonds. So hydrogen bonds, that would be false. Chemical bonds include ionic bonds and, you guys, covalent bonds.